Today, I'd like to talk about development of new inkjet head applying MEMS technology and thin film actuator. This is the contents of my presentation. I'll talk following this order: introduction, simulation method, manufacturing prototype print heads, comparison of simulation and experiment, utilization of simulation model, and conclusion. At first, I'd like to introduce our company and our latest products briefly. Konica Minolta Inc. has long experience in inkjet industry. We develop and sell not only printhead components, but also inkjet printers, like textile printer, Messenger, and wide format single pass printer, KM1. And for those products, we used shear mode type piezoelectric printheads. But recently, we introduced new inkjet printheads adopted MEMS technology. This is the specifications of our new heads, and you can find this specification sheet on our website. We had three lineups: ME130H, which has 1200 NPI resolution; MC160H, which has 600 NPI resolution; and for ML160H, which can apply two colors in one head by 300 NPI resolution. Okay. This is our latest product, and we are going to start mass production of these products from next spring. Okay. Today, I'd like to talk about not this product, but our future generation printhead, because this is our first generation MEMS head, and I'd like to introduce on this time our next generation MEMS head. For next generation printheads, higher performance, like higher number of nozzles or higher resolution, and additional functions like ink circulation system near the nozzle, are demanded. And we think MEMS technology and thin film actuator could be the solution for that. Why MEMS and thin film actuator? The combination of thin piezo film on silicon wafer and MEMS process has many advantages. We need no actuator assembly process by applying photolithography method. High crystalline thin piezo film can achieve high speed drive and high uniformity. And integrated MEMS process can achieve small size and high nozzle density printhead with low manufacturing cost. Small size means we have more space in actuator plate, so we can add some new functions like ink circulation. This is the purpose of this work. High quality inkjet printer requires jetting properties like below: high jetting frequency around 100 kHz, small droplet size around 2 picoliter, and possible to use high viscosity ink around 10 millipascal sec. We tried to establish a method to design thin film MEMS head by building a simulation model and manufacturing prototype thin film MEMS heads and verifying the observed properties and calculated ones. Okay, next part is simulation method. In this section, I'd like to explain about our simulation model. Piezoelectric inkjet head is generally divided in two parts: actuator part and ink flow channel part. These parts are combined each other when printhead ejects a droplet. Then coupled analysis is needed. For treatment of the coupled behavior, we applied equivalent circuit model by replacing actuator and ink flow channels into electric circuit. The behavior of an electric charge in electric circuit is described in this equation, and mechanical behavior of the actuator is described in this equation, and acoustic behavior of ink flow channel is described in this equation. These three behaviors are described in the same equation form. Then we can replace each other equivalently. This table shows the correspondence of parameters in each field. This is the basic equivalent circuit model. We built a model by replacing an actuator and flow channels into electric circuit. We can calculate jetting properties from this part and actuator oscillation properties from this part. We designed actuator and ink flow channel dimensions to optimize the jetting properties. Next is manufacturing prototype printheads. In this section, I explain how we manufactured our prototype thin film MEMS head. 3 years ago, we released 1 picoliter MEMS head for digital fabrication use. We modified this former released 1 picoliter MEMS head and manufactured a test piece. We use the same parts except this MEMS head chip. MEMS head chip consists of silicon actuator plate, glass intermediate plate, and silicon nozzle plate. And these 3 plates are manufactured by MEMS technology. We changed the shape of pressure chamber and nozzle and replaced piezoceramic element with thin piezo film element. This is schematic illustration of an individual channel. Ink is introduced from the reservoir to the pressure chamber through the inlet and ejected from the nozzle by thin piezo film actuator. This table shows the manufacturing process of thin film actuator. At first, lower electrode was deposited on silicon substrate. Secondly, thin piezo film was deposited on that. Thirdly, upper electrode was deposited and patterned. Next, thin piezo film was also patterned and lower electrode was patterned. Finally, a part of silicon substrate was removed by silicon deep etching method and diaphragm was formed. This is the appearance of thin film actuator of our prototype printhead. This is microscopic image and this is SEM image. Upper square part shows the bonding pad for testing and lower circular part is an actuator part. The silicon substrate opposite to this circular part was removed. This imposed figure shows the cross-section of thin film actuator. The thickness depends on the jetting properties, and for high viscosity ink, we need from 2 to 5 micrometer to generate high pushing power. As shown in this figure, we succeeded to produce test pieces accurately by applying MEMS manufacturing process. This is the fundamental waveform we applied for our experiment. We applied full push drive. At first, application of voltage V1 constructs and deforms the actuator. And next part pulls the actuator and ink is introduced. And then final part pushes the actuator and ink is ejected from the nozzle. This picture shows the jetting condition of single nozzle. The horizontal axis means time. We use solvent ink with 10 millipascals viscosity and drove 6 meter per sec at 15 kHz. We observed no satellites with a normal push drive. Next is comparison of simulation and experiment. This table shows the jetting properties of simulated one and measured one. We designed two different actuator types, small size droplet with high frequency type and large size droplet type. The former one was designed for jetting frequency 71 kHz and droplet size 3 picoliter. And later one was designed jetting frequency 45 kHz and droplet size 6 picoliter. As shown in this table, the measured results corresponded well with the calculated ones. That means our simulation model can predict the jetting properties precisely. Okay. Next, to investigate the specific actuator properties, we observed the actuator oscillation properties by laser Doppler vibrometer. This is the observation model, and we use glass plate as top cover of the prototype head, and that enabled us to observe the actuator oscillation during the printhead jetting the droplet. This graph shows the actuator oscillation of simulated and measured one, respectively. The upper line shows the shape of actuator oscillation when this driving pulse was added. Okay. This vertical axis means displacement of the actuator, and this is the driving voltage. And horizontal axis means time. Okay. As shown in these graphs, the simulation was able to reproduce the measured actuator oscillation shape, even the reverberations. Okay. Then we used this measurement to optimize the driving waveform. These reverberations interrupt the next jetting pulse when we use the printhead with high frequency. For example, if we use frequency higher than 50 kHz, the next jetting pulse will come around this timing. Then we need to eliminate the reverberations. We applied cancel pulse to eliminate the reverberation in this timing. We optimized the cancel pulse shape and timing to eliminate the reverberation by observing the actuator oscillation directly. By using optimized waveform, velocity change was suppressed even in the high frequency region. And we succeed eject droplets with 70 kHz stably. Okay. And the actuator oscillation also gives information about inside of the ink channel. We observed irregular actuator oscillation at the nozzle ejecting droplets unstably. This graph shows the regular oscillation and irregular oscillation. The applied driving pulse was same. In this graph, the irregular actuator oscillation shows higher frequency than regular oscillation. Okay. We analyzed why this phenomenon occurred. We calculated the actuator oscillations when an air bubble was inserted in several parts of the ink flow channels. And our simulation clarified the irregular actuator oscillation was due to the air bubble in front of the nozzle. In such case, the oscillation shape itself wasn't changed from the original one, but the frequency became shorter. And we think we can apply this kind of technology to detect a missing nozzle. Okay, this is conclusion. We confirmed suitability of equivalent circuit model simulation, possibility of high-speed and high-resolution inkjet printhead, and usefulness of our simulation model for analysis. We succeeded in producing a new inkjet printhead with MEMS technology and thin film actuator by designing the printhead with our simulation method. So in the future, we will develop a novel MEMS head with high nozzle density and additional functions by arranging thin film actuators two-dimensional. Okay, this is the end of my presentation. Thank you very much.
Mawatari-san, thank you for your presentation. I have a couple of questions.
Yes.
You're running here this simulation. Yes. Am I correct that you are thinking about a MEMS implementation in bend mode, so that you're going away from the share mode and then you move to a bend mode implementation?
Ah, yes. This is bend mode, so we applied bend mode simulation. Excuse me, what do you mean?
No. I was just trying to confirm for the audience that this is a bend mode implementation.
Yes, this is bend mode.
Formerly you had, let's say, share mode, just like XR had, and now you're moving into a bend mode implementation for MEMS.
Yeah, that's right.
Yeah. When you talk about higher nozzle density, what kind of density are you thinking of? If that's the 1200?
Well, yeah. Our current model, first generation MEMS head, already has 1200 NPI, but it has only 1024 nozzles.
Okay.
So, yeah,
physical nozzle 1000.
Yeah, increase that.
1200 then times 600?
Yeah, we are considering about that now.
We are also always looking also, yes, you've run the simulation model with, let's say, solvent-based ink. What's the final ink going to be here?
Well, yeah, finally, we have to test all kinds of inks, our prototype head. But for
water-based?
Yes. Yeah, I think we can also use water-based ink because our first MEMS head can use aqueous ink, which means water-based ink.
Water-based ink, UV ink?
Yes.
Okay, basically we're talking here about manufacturing process. Another question on the drop volume.
Yes.
You showed us 1 picoliter, 2 picoliters, 3
yeah.
picoliters, 6 picoliter. Will this be a one version, let's say 6 picoliter, with multiple levels, or will it be just a single upfront chosen picoliter size?
In this presentation, I showed just one droplet size, so one droplet for 3 picoliter or 6 picoliter. So we can use grayscale and increase the droplet size from base this. For example, for this model, for this type, the 1DPD is 3 picoliter, so you can use grayscale and increase the droplet size.
Will the new head be announced at Drupa then, 2016?
Well, yeah.
Launched?
I'm not sure.
You're not sure yet. Okay. Are there any questions from the audience?
Thank you. Have you done simulations about the life of the printhead, the life of one nozzle?
Well, in this equivalent circuit model, it's difficult to simulate the lifetime. So we use the manufactured prototype head to analyze the lifetime of the actuator. And we confirmed, I think, let's say, 10 billion shot, after 10 billion shot, the velocity change was less than 10%. So I think, yeah, it's okay.
Yes, another question?
Okay, thank you. I think my question is also related because I noticed the driving voltage is pretty high, 29
yes.
volts.
And
whether this means the life is short of the...
That's due to the, let's say, modeling of the prototype head. We used the same parts and only changed these parts. So the driving voltage is not optimized for this study.